Take any car around a corner, the four wheels look like they all move together. They don't. The wheel on the outside of the turn travels along a wider arc. It must roll farther and faster than the wheel on the inside. Yet both are joined to the same engine, the same spinning power. So how do they turn at different speeds without tearing the road apart? Let's slice open the small part that quietly solves it. Picture a single straight rod linking the left and right wheels. On a straight road, that is fine. Both wheels spin at the very same rate, but enter a curve, and the outer wheel now has more ground to cover in the same moment. Locked to its twin, it cannot. One wheel must drag, scrub, and chirp across the pavement. You feel it as a hop, a stutter, a fight between the tires. The car wants to go straight when you want to turn. Think of two runners on a curved track. The one in the outer lane has to cover more ground than the one on the inside to round the same bend. To stay side by side, the outer runner speeds up while the inner one eases off. Your car's wheels face this exact problem in every turn. The puzzle for engineers was mechanical, not human. How do you let two wheels choose different speeds, while a single engine still drives them both at once? Power leaves the engine and travels down a spinning shaft toward the rear of the car. At its end sits a small cone-shaped gear called the pinion. The pinion has one job, carrying the engine's rotation onward to the wheels. But it points the wrong way. The shaft spins front to back, while the wheels must spin side to side. Somewhere in here, the whole direction of motion has to bend by 90 degrees. That turn is the very first trick. The pinion bites into a large disc ringed with teeth, the ring gear. As the small pinion spins, it walks around the edge of the big ring and forces it to rotate. Two things happen at once. The motion bends 90 degrees, now spinning in line with the wheels, and the gearing multiplies the engine's twist into something strong enough to move a heavy car. Bolted to that ring gear is a sturdy steel cage. When the ring turns, the cage turns with it. This cage is the heart of the differential. Engineers call it the carrier. It does not simply spin as a solid lump. Tucked inside it is a small cluster of gears, free to move in a clever way. Imagine a tiny merry-go-round bolted onto the ring gear, carrying a handful of gears along for the ride. As the whole assembly whirls around, those inner gears are about to decide how the engine's power gets shared between the left wheel and the right wheel. Inside the cage sit two kinds of gears that mesh face to face. Two small ones, called spider gears, ride on a pin fixed across the cage. Two larger ones, the side gears, point outward, and each one connects to an axle that runs out to a wheel. The spiders sit between the two side gears, touching both of them at once. Through that little knot of teeth, every bit of power must pass on its way from the cage out to the wheels. Now drive straight ahead. Both wheels meet equal resistance, so both want to spin at the very same speed. The side gears hold still relative to the cage. The spider gears, caught between them, feel no reason to turn on their own pin. So the entire cluster rotates as one locked block, spinning with the ring gear. Power flows evenly, left and right, and the spiders simply ride along, going for the spin without ever rolling themselves on the pin. Now turn the wheel. The outer wheel needs to run faster and the inner wheel slower. The instant they disagree, the spider gears come alive. They begin to roll on their pin, walking along the teeth of both side gears at once. As they roll one way, they feed extra speed to the outer side gear and pull the same amount away from the inner one. The wheels are finally free to spin at different rates, with no dragging and no scrub. Here is the quiet brilliance of it. The differential never changes the total. Whatever speed the outer wheel gains, the inner wheel loses exactly. Add the two wheel speeds together, and you always land on the same number, set by the cage. So the engine feels a steady average pace, while the wheels below quietly negotiate their own. No sensors, no computer, just gears feeling the road and sharing the difference between them, moment to moment, turn after turn after turn. But this freedom has a price. An open differential always sends power to the wheel that spins easiest. Lift one wheel onto ice, and that wheel happily spins while the wheel with grip sits dead still. the car goes nowhere. To fix it, engineers add limited slip clutches or locking gears that force both wheels to share the load when grip runs out. The same cleverness that frees your wheels in a turn can also strand you on a slick road. So follow the path once more. Power spins down the driveshaft to the pinion. The pinion turns the ring gear 90 degrees and bolts its motion to the cage. Inside the cage, spider gears and side gears mesh together. Going straight, they lock and split the power evenly. Through a curve, the spiders roll, speeding the outer wheel and slowing the inner one by the same amount. The total never changes, a handful of gears quietly solving a problem in every corner. A car turns 1,000 corners and never once complains. Beneath the floor, a small cage of gears is quietly doing the math for you, splitting power, balancing speed, and asking nothing in return. Next time you round a bend, notice how smooth it feels. That is the differential, working perfectly, inside a part you will probably never see. We will see you in the next cutaway.